Today we're going to first characterize completely optimal strategies and the value of the game. We've already talked about these in past lectures, but we want to make this precise now for a general finite two-player zero-sum game. So for just a general finite game, we have an m by n matrix A. M by n means here we have m choices for player 1. Remember, player 1 plays one of the rows, so we have m choices for the different rows and n choices for the different columns. Now, how are we going to characterize a strategy? When we talk about a strategy, we'll talk about a mixed strategy. Think of this vector p, and in the book we write that typically as a column vector, so the vector will be p1, p2 through pm. These have to be the probabilities for picking each row. Remember here, since these are the probabilities, we need p1 plus p2 up to pm always to be equal to 1. And similarly, player 2, this would be for player 2, I didn't write that correctly. For player 2, we have a column vector q1 through qn, and just as before, we need q1 plus q2 up to q sub n equals 1. So this is what we mean by a general mixed strategy. If all of these are 0 except for a single one, then of course that would be a pure strategy in the particular row or a pure strategy in a particular column, but in general we'll be talking about mixed strategies. What characterizes optimal strategies and the value of the game? Well, for this vector p to be an optimal mixed strategy, we need player 1 to be guaranteed a result at least v, what we claim to be the value of the game, no matter what player 2 does. That means for any choice of a column, let's say just as an example, player 2 chooses column 3, we would need for any choice of a column, the expected return, in this case it would be p1 times a13 plus p2 times a23 up to pm times am3, has to be at least v. Well, that's what we're saying here by saying the sum from I equals 1 to m of p sub I, a sub I, j is greater than or equal to v for all j equals 1, 2, 3 up to n. Here, when we chose column 3, that would just be putting in here j equals 3. For each different column, j equals 1 through n, we have a statement that says the expected return is at least v if player 2 plays that column j. Now, at the exact same time, for q to be an optimal strategy for player 2, we need the expected return for player 2 to be no worse for player 2 than v. And what does that mean? That means less than or equal to v, no matter what row player 1 plays. So we can express that as saying the sum from j equals 1 to n of aij times q sub j is less than or equal to v. That's true for I equals 1, 2, 3 up to m. For example, if I equals 2, just look here what that would say. The sum of a2j times qj is less than or equal to v. Well, in row 2 here, if player 1 plays row 2, the expected return is exactly a21 times q1 plus a22 times q2, etc. That's exactly what we have here. And we have that for each row, for each I equals 1 to m. So we need a whole bunch of things to be true. For every possible column player 2 picks, player 1 expects at least v. For every possible row that player 1 picks, player 2 expects at most v, meaning at least as good a result as having v. When all of these are satisfied, then we know v is the value of the game. Because each player can play a strategy that guarantees at least a return at least as good as v, greater than or equal to v for player 1, less than or equal to v for player 2. And of course, these strategies, p and q, are strategies that will achieve the value of the game, and that's what we mean by optimal strategies, because there's no strategy that can guarantee a better result than that. Now, in general, it's going to be tough for us to find optimal strategies. We've already talked about this for 2x2 games, and we've seen examples of how you compute this for 2x n or m by 2 games. In all those cases, the technique in the 2 by n and m by 2 games, you can use the techniques we've discussed always to find the actual value of the game, and you can find the optimal strategies. But in general, it can be very difficult. You can use domination, and you can remove dominated rows and dominated columns, and you can do that successively if that's possible to reduce a game to a simpler one. But there are going to be times when that still leaves us a situation where it's hard to find the exact value of a game and what the exact optimal strategies are. Here's some examples where things are very simple. And they're just kind of fun examples. They're not general by any means. It's only lucky if such a thing comes up. We're going to talk about Latin square games. What do we mean by a Latin square game? Well, a Latin square is an n by n matrix filled with n different symbols, each occurring exactly once in each row and exactly once in each column. The game we've looked at most, the rock, paper, scissors game, has 3 choices for player 1, of course, and 3 choices for player 2. It's a 3 by 3. It has a 3 by 3 payoff matrix, and this is just a Latin square with the three numbers 0, 1, and -1. You see each row and each column has exactly 1 0, has exactly 1 1, and exactly 1 -1. Here's an example of a bigger Latin square, a 4 by 4 example, where we use the numbers -1, 1, 2, and -3. And you'll see that every row has these 4 numbers, and every row like this, and every column has these exact same 4 numbers. Now, is it easy to solve? Well, we've already seen how to solve the rock, paper, scissors one, and you might guess that it's similarly easy to solve this one. There's a simple claim that will let us solve Latin square games. I claim in a Latin square game, each player has an optimal strategy that consists of 1 over n's. This is for the n by n game, so there are n entries, each 1 over n. So you see the total probability is 1. And the value of the game will be exactly the average of the entries in any row, or the average of the entries in any column, which of course will be the same thing. Why is that true? Well, in such a situation, regardless of which row, let's say, for example, we're looking at player 1. If player 1 plays this strategy, then regardless of which column player 2 picks, the expected return will be 1 over n times the first entry in the column plus 1 over n times the second entry, up to 1 over n times the nth entry in that column, which will be exactly the average of the entries in that column. And since every column contains the same n numbers, that will be the same for every column. So that average of the entries in any column will be a number v, which will be the expected return no matter what player 2 does. And in exactly a very similar argument tells us that if player 2 plays this strategy, the expected return will be exactly that same value v, the average of the entries in a row, which is the same as the average of the entries in a column, no matter what row player 1 picks. So it's a very simple thing to see that you have very simple optimal strategies and a very simple value for the game. If we go back here, we already knew that for rock, paper, scissors. The value, of course, we found is 0. That's just the average of the entries in any column or any row. And the optimal strategies are just going to be 1/3, 1/3, 1/3. That'll be optimal for each of the players. And we've already discussed that quite a bit. So for this game, if player 1 plays a row here and player 2 plays a column, the value will be the average entry in any row or any column. You can see that when you average these numbers, -1, 1, 2, and -3, they sum to -1, so the value will be -1/4, and the optimal strategies for both players will be exactly 1/4, 1/4, 1/4, and 1/4.